Okay. Right. Right. So I'm not Yanbei Chen. I hope that's clear. And I guess we'll hear from Yanbei in a minute. Can everyone hear me? Okay. uh, and so, okay. So what I'll be talking about today, well, is this. Well, I was asked to speak. When I was asked to speak at this conference, I was trying to think about what kinds of things would be, of interest to this very broad community, and I decided to actually revisit something that I did in my PhD with Dane Danielson, who's in the audience, and Bob Wald, who was my advisor at the time. And the particular references that are of most, that are most relevant for this talk are this one here, the one highlighted in blue, and in particular building on this paper by Bob, Alessio Belenchia, and these co-authors you heard from Marcus earlier this week. And those are really going to be focusing on the Newtonian fields and gravitons part of this talk. At the very end of this talk, I'll mention a kind of twist on this story with black holes. That'll be at the very end. That's actually going to start or motivate Dane's talk, which will be tomorrow. Okay, those references for the black holes are highlighted, are in black. Okay, but so let's just get started with just thinking about, everything I'll be talking about today are Gedanken experiments in quantum gravity. Gedanken experiments and actual experiments are things that you guys have been thinking about, and in particular in the context of quantum gravity, people were seriously thinking about these Gedanken experiments as early as the late 1950s. Well, this was already referenced multiple times, in this conference, this famous Chapel Hill conference, though this particular quote I don't think has been particularly mentioned. And, so people like really serious people like Wheeler, DeWitt and others were kind of all at this conference, and they were debating what the kind of fundamental mathematical and conceptual structures are for a quantum theory of gravity. Feynman, it's really useful to look through those, the transcript. I recommend reading the whole thing, because at one point, Feynman is kind of uncharacteristically quiet, for most of this transcript. But at some point, he just interjects essentially, and you can really imagine him interjecting in, this kind of, like frustrated way, and really saying that, well, I don't know essentially what the fundamental properties of such a theory is, but it would be useful to probe the properties of quantum gravity by considering situations where both quantum theory and gravity play an essential role. Okay? And that's not something I need to convince this audience of, obviously. I mean, this was a Gedanken experiment at the time of Feynman, but it's now a real proposed experiment that has been, considered since 2017. This is a cartoon that I took from Dan and Philip Stamp's paper of a mass now in a spatial superposition. And what I'll be essentially doing in this talk is using such an idea of a mass put in a spatial superposition, but taking it out of the realm of the context that you guys are doing in your experiment, and really just studying this at the level of Gedanken experiments to really answer this question. Okay? So what aspects of the quantum theory of gravity can we learn from such Gedanken experiments? Okay? So just in the spirit of Feynman's original ideas. And then we'll come back at the end to the experiment that you all are actually doing at the end. Okay? Yeah, if there are like questions about the setup or whatever, I know you're not supposed to interrupt me, but just feel, I don't know, like, don't keep doing it, but if you have, I want everyone to be on the same page. Okay, so what am I going to do? Well, I'm going to consider, like any Gedanken experiment, you need an Alice, and later we're going to introduce a Bob. Okay? So what is Alice doing? Well, Alice has a very difficult PhD ahead of her. Some of you might be able to commiserate with this. So what she's going to do, and there's an electromagnetic version of this Gedanken experiment, and later we'll do the gravitational version. It's useful conceptually just to do the electromagnetic version first. And Alice, therefore, is going to be controlling a charged particle, okay, with spin. That should sound familiar. And at some time, at the beginning of her PhD, she has a huge success from your eyes, which is that she's able to make a macroscopic spatial superposition of her charged particle. Yeah, some of you in the audience are, your eyes are wide at this stage. Just wait until you get to the later, especially with the black hole. But okay, so what she's going to do is she's going to pass her particle through a Stern-Gerlach apparatus. So if her particle was initially aligned in the x direction, she's going to pass it through a Stern-Gerlach apparatus, let's say oriented in the z direction. That's going to make a 50-50 spatial superposition, A1 and A2 being the wave function of her particle either going to the left, let's say with spin up in the z direction, or going to the right with spin down in the z direction, as depicted here, and I've depicted a 50-50 one just for simplicity. Okay. So that's a major achievement, but she's nowhere close to finishing her PhD, because what she then has to do, this is, she's at a really tough institution, she has to maintain this superposition for her entire duration, let's say, of her PhD, and then, when she's done, let's say at her committee meeting, she's going to recombine her particle, and we'll tell, the time from her committee meeting to her defense is, let's say, a time TA. In her lab, she's going to recombine her particle, and she graduates if her particle has maintained coherence. Okay. So that's really hard, but she's a really good experimentalist, and she's going to try to control for all environmental factors that you all have to deal with. Okay, so this is a space-time diagram. Alice started her PhD way, way, way in the past. This is not even depicted in the diagram. After separating, she's maintained the center of mass trajectories, which is what's displayed here, of her particle for this duration of time, and she's at this fixed spatial separation d, and at this time that, let's say at her committee meeting, she reorients her Stern-Gerlach and passes the beams of her particle through the Stern-Gerlach apparatus, reversing Stern-Gerlach apparatus, and then checks the coherence of the particle. How would she check the coherence of the particle? Well, she could just measure the x spin. Originally, it was definite spin up in the x direction. She would just measure the spin in the x direction. If she ever sees spin down in the x direction, she knows she can't graduate. If she sees spin up, if she sees spin up, she doesn't know she's maintained coherence, but she could do multiple PhDs, obviously. Okay? So why is she worried about that? Alice is a really good experimentalist. Why would she even be worried about loss of coherence? Well, she's worried about it because she has an office mate, Bob. Okay, and Bob is jealous of Alice and her ability to maintain coherence and wants to destroy Alice's coherence. And what he realizes that, yeah, Alice can cool down the room, Alice can do lots of nice things, but she's neglected to control the Coulomb field of her particle. Okay? And so what he's going to do is, over in a different lab where the Coulomb field has had its time to go enter into that lab, he's going to release a test charge. And so what his plan is by releasing the test charge, it should get deflected differently depending on if it's feeling the influence of Alice's particle having gone to the left or having gone to the right, and thereby entangle with Alice's particle and therefore destroy her coherence. It's a pretty good idea, and since Alice has unfortunately neglected to control this long-range field, Bob over here, he has a particle initially in a trap. It's initially unentangled with Alice's superposition. He's going to release the particle from the trap, and that's going to get displaced differently depending on whether it's feeling the influence. Let's say it's negatively charged and Alice's thing is positively charged. Then it's going to get displaced differently if it feels the influence of Alice's particle over here or over here. Does everyone understand the setup of the Gedanken experiment? No. Finite time in the past. I just haven't depicted the time in which she's made the separation. This is inside the light cone of the Coulomb fields. Yeah, so this is inside the light cone of the path separation. Yeah. The Bob particle does not have spin, it just needs to feel the influence of the Coulomb field. Okay, so this is a great idea, and certainly one that is going to destroy, I mean, he can certainly get which path information, some information from this protocol. Okay, the twist is that Bob is going to perform this. He doesn't want to get caught. Alice is watching him like a hawk, and he does not want to get caught by doing this experiment at any time-like separation from Alice's protocol. Why doesn't he just go over and do this at space-like separation? As was just mentioned before, the Coulomb field of Alice's particle has already set up at space-like separation from her recombination. Okay, it's already set up over here. He should be able to release his particle, and it will get displaced differently, whether or not the Coulomb field had gone to the right or gone to the left. So he should be able to do this measurement and distinguish the different Coulomb fields over here, and he doesn't want to get caught, so he's going to do this protocol at space-like separation. So just to give you a diagram, that's the situation of interest where I've drawn in now the light cones. So the Coulomb field, again, is already all set up here at space-like separation. Bob, at that exact time, is going to then release his test charge, and it's going to get deflected differently. And for sure, if Alice's separation is big enough, or the charge of her particle is big enough, it's going to get enough displacement that he should be able to distinguish the individual Coulomb fields at space-like separation. Okay, so this is all set up to get you bothered, and this is the exact kind of thing that a physicist, listening to this is going to get, really bothered by, because this is a clear violation of causality. Whatever Bob does over in this region should have no influence on the coherence of Alice's particle. Bob could sleep in that day and decide to not open his trap. Then Alice's particle should not be influenced by whether or not Bob had made a measurement. Whereas if Bob decides to release this particle, he will be able to get some which path information and thereby influence or decohere Alice's particle. So what's going on here? Does everyone understand the nature of this paradox? Okay, so this paradox was, considered by Marie de Palma and Giovannetti and collaborators, but it was correctly analyzed, in the gravitational case, which we'll get to in a second, by Belenkia and others, and I'll be reviewing now what their resolution of this paradox is, which is that both Alice and Bob are coupled to a quantized electromagnetic field. And there are specific features of the quantized electromagnetic field that, because the QED is a causal theory, so there must be certain features of this theory that are important for the resolution of this paradox. And the key idea is that we want to isolate what are the key features of that theory. So these features are going to place fundamental constraints on both of their ability to perform this experiment. Okay, so this is the most complicated expression that you're going to see in this talk, so we're just going to go through it one step at a time, but hopefully it's not that complicated. So Alice has to recombine her particle within a light travel time from Bob. She's got to, if Bob is any moderate distance away, she has to recombine her particle very quickly by those standards. And if psi1 and psi2 are the radiation states from path 1 and path 2 of her particle, she's going to just emit some electromagnetic radiation on her own. She's got to recombine her particle back together. And if the decoherence is determined by the orthogonality of these radiation states. This is now just what is the decoherence of Alice on her own, even if Bob wasn't there, just her doing her PhD on her own. And that is determined by the expected number of photons. It's the expected number of photons in the so-called difference of the radiation states. Those are the photons that determine which path information. So the radiation state from path 1 and path 2, you take their difference and you compute the number of photons in their difference, and by simple Larmor formula type estimates, you can determine from her protocol what the number of photons emitted are. It's determined by the essential effective dipole of her superposition, Q times the separation, over the time scale that she does this experiment. Okay, so even in the absence of Bob, just by constraints that she's coupled to an electromagnetic, a quantized electromagnetic field, she must recombine sufficiently slowly so as to not decohere herself. Okay? So what is Bob influenced by? Well, he's again also coupled to the electromagnetic field. And Bob, by being coupled to the electromagnetic field has vacuum fluctuations in it. He's trying to do a sensitive particle displacement measurement. So by coupling his particle to the electromagnetic field, he's doing that by Lorentz force. The fluctuations of the electromagnetic field are going to give rise to fluctuations of his test charge. And so therefore, he's not going to be able to resolve the displacement of his particle if it's under this just universal displacement just due to vacuum fluctuations alone. What is such a universal displacement? Well, you can just work out. I won't do it for you here because I want to get to other stuff, but the fundamental vacuum fluctuations influenced by a test charge, if you average the Lorentz force equations just due to the vacuum fluctuations, is just determined by the ratio of the charge to mass ratio of Bob's body. And when you say that when you want that the displacement of his test charge due to the influence of the Coulomb fields is bigger than a vacuum fluctuation, so that he can actually get which path information, you find the following constraint on Bob's protocol. You don't need to see that this is the implication, you just have to see that Bob has to integrate his experiment for a sufficiently long amount of time to beat out the vacuum fluctuations. That's the idea. Okay. What this was argued in this paper was that both inequalities cannot be satisfied at space-like separation. So if Alice can maintain coherence, so if she does her experiment slowly enough, let's go back to the diagram. So if she does her experiment slowly enough, you can imagine enlarging this diamond, right? But if you enlarge this diamond, you shrink the duration over which Bob can do his experiment, okay? Which means that he cannot beat out vacuum fluctuations. Whereas if you give Bob enough time to do the experiment, given the protocols of Alice's experiment, then what by these inequalities imply is that the diamond is too small, and she's got to decohere herself. So if Bob has enough time, then Alice must decohere by entangling radiation. Okay, and so that's the electromagnetic version. The gravitational version is almost identical. So what was essential in the electromagnetic version? The two key features in order to avoid violations of causality and complementarity, the two key features of the electromagnetic field that we needed was quantized radiation that can entangle with Alice's particle, as well as vacuum fluctuations. Those are both key features of the electromagnetic field that was necessary to avoid these contradictions. Okay, so now I'm just going to go over, the exact lessons and everything go forward in the gravitational case with just slight modifications. So I'm just going to explain the slight modifications, but essentially you should be thinking along almost the exact same lines in the gravitational case. So in the gravitational case, we treat everything almost analogously, where both Alice and Bob, they don't need to have charged particles now, they just have massive bodies. Okay, one is a superposition of a massive body, and Bob is just releasing a test mass. Okay, so what is the which path information? So one key distinction that Belenky et al. Point out is that the which path information is not going to be contained in the mass dipole of Alice's superposition, because you can't make a gravitational dipole. If you make a superposition, Alice's lab is going to, make a dipole, Alice's lab is going to get displaced in the opposite direction. The real which path information is obtained in the effective quadrupole of Alice's superposition. And Bob can succeed, so the quadrupole is entering in this term right here, m times d squared now, as opposed to q times d from before. And Bob, you can find, succeeds in his measurement if he can beat out his displacement beyond a vacuum fluctuation. Now the fundamental vacuum fluctuations of the quantized gravitational field are on the order of the Planck scale. And that implies that he has to do his experiment for sufficiently long in order to beat out these vacuum fluctuations, and this is exactly how long he has to do it, or roughly speaking. Okay, good. To avoid decohering herself, Alice has to avoid the emission of gravitons now while she recombines her body. And this is now the quadrupolar radiation that she's going to be emitting, and now this implies a fundamental limit on the time duration of her protocol. She needs to do her experiment sufficiently slowly on her own in order to avoid emitting entangling gravitons. And again, you find that these inequalities cannot be satisfied if they both do their experiment at space-like separation. Okay. So the analysis essentially and conclusions parallel the electromagnetic case, where the difference is that you just replace the word dipole everywhere with quadrupole, okay? In exactly the same way before. And now the lesson from this, which may be of relevance to this audience, is that if you have a superposition of a massive body, and you want to avoid any contradictions with causality and complementarity, the key features of the gravitational field that are essential to avoid such contradictions are the quantized radiation of the gravitational field and the inherent vacuum fluctuations of the field. What's my time, by the way? Okay, great. So what are the, so this was work that was done prior to my, when I entered this discussion. And this work is really showing you what are the key features of the gravitational field essential to avoid these contradictions. However, there are some, at the risk, it's a very nice paper, but at the risk of pointing out any deficiencies at all, let me just take the slide to do so. So while the above, this analysis is really pointing out the key features of the gravitational field, these arguments were done kind of at just a back of the envelope analysis. All of these inequalities that I wrote down should come with these tildes, expressions. These are just saying that there's no obvious contradiction. It's not really saying that Bob can't get any witch path information from doing a protocol of this kind, and in order to claim that there's no violations of causality, one would have to really say something much stronger than that. Okay, that's one point. Well, and also, this protocol was kind of focused on this particular particle displacement measurement of the gravitational field. Well, it's not obvious, for example, Bob can't do better, by buying a better apparatus, or in particular, hiring some more assistants. Like, for example, yes, okay, this particular Bob we showed failed, but what if I put another Bob over here, okay? And I should have mentioned this Bob is not Bob Wald, this is a skilled experimentalist who can hire many graduate students, and what he's doing is they're releasing these test masses, and individually they might fail, but they might be able to do better by doing joint measurements of Alice's superposition. That's not so obvious because the gravitational field is also not just fluctuating, but highly entangled, right? So this is a correlated measurement with this measurement, but the correlations of the gravitational field were not taken into account in the previous discussion, right? Just the local fluctuations. So you would have to redo a completely different kind of analysis to study this scenario. And you could make more and more complicated scenarios, giving Bob more and more different apparatuses. Okay. So what we're now going to prove in the final 20 minutes of this discussion is that there are absolutely no violations of causality that can occur no matter what measurements Bob can make. Okay? And this is not an entirely academic exercise. What I would like to really understand, the reason I became interested in this paper in the first place, the one that did this analysis and the electromagnetic one, is that what this seemed to be suggesting is that there is a fundamental relationship between decoherence and causality. And what I would really like to understand better is what exactly is that relationship, and can one make that even much more precise? And hopefully later we can then take that to the bank and study other situations outside of even this context. So let me do that in the final time that I have. Well, in order to do that, we kind of have to go back and redo a little bit better the decoherence that I was analyzing for both Alice and Bob. So let's go back now and study just the decoherence of Alice's particle in the absence of Bob. Okay. So the components of her particle, when the components of her particle are separated, during the separation process, there isn't really an unambiguous description of the Coulomb field and the radiation that that's coming along for the ride. Maybe she emitted a little bit of radiation earlier on and so forth. There really isn't an unambiguous distinction between the two, just because you have two separated components of the particle. You could try to ascribe you could try to fix some gauge or something like that, but there's no covariant distinction between the two. However, after the recombination, the components of her particle share a common Coulomb field. So what one can do is, after the recombination, one can simply subtract out this common Coulomb field, and what you have after the recombination is just source-free electromagnetic field, after you subtract out this common Coulomb field. So I'll explain what that means in a second, or I'll show you a diagram. But on any, what I'll call Cauchy surface, any time, but I'm a relativist, so I'm allowed to draw time in any way I want. Time is just a surface, right? So on any surface, after the recombination, the total quantum state with this kind of common Coulomb field subtracted is Alice's particle having gone to the left and now recombined, tensor the radiation emitted by this particle, plus Alice's particle having gone to the, I guess I must have messed up my left and right. Alice's particle having gone the other direction and recombined, and having emitted any radiation she emitted during that process. That's a completely invariant description at this time. And psi1 and psi2 are genuine radiation states, which contain all of the Witch path information of Alice's particle. Okay? And again, I warned you I'm a relativist, so I get to draw time however I want, and I decided to draw it in this kind of funny way to emphasize that at any time after the recombination, P is the recombination, I can subtract off this common Coulomb field of the electromagnetic field, and all that's left of the electromagnetic field now are the two radiation states that I just mentioned before. And if I just take their inner product, that tells me how orthogonal the states of Alice's particle, or the radiation states of Alice's particle are, and how decoherent she is due to her own emission of electromagnetic field. This is the exact same formula I gave you before, and this is valid at any time after the recombination. And this, I've drawn a space-time diagram. I won't unpack it in a lot of detail. I've just made Minkowski space finite in order to draw this. This is where she started the experiment, or this is where the particle came in. She started the experiment, let's say, sometime here. She separated them and then recombined them here. You can ignore the infinity and things like that. That's just if you're not familiar with that terminology. Okay, so what's the decoherence due to Bob? Well, let's consider now, in order to isolate just the decoherence due to Bob, consider the case where Alice recombines the particle really, really slowly and emits negligible radiation. Okay? So let B be the initial state of Bob's particle, B naught, this be the initial state of Bob's particle with, and this could be, or I'm saying particle, but I really mean apparatus. This could be initial state of any quantum state of Bob's apparatus of him and any number of assistants, which is initially unentangled with Alice's particle. So this is the initial state that we have of Alice and Bob. Alice has her superposition, and Bob is just tensored in. Okay? Due to the interaction with the Coulomb or Newtonian field of Alice's particle, after Bob releases, allows his apparatus to interact with Alice's particle, Bob's apparatus will evolve to B1, let's say, if Alice's particle had followed path 1, or B2, you know, this other quantum state, if Alice's particle had gone on path 2. So the quantum state after the evolution of, joint evolution of Alice is just sitting there, or she's recombining very slowly, and Bob is of this character where B1 becomes correlated with path 1, and B2 becomes correlated now with path 2. Okay, so I hope everyone's following along. The decoherence at any time where Bob's apparatus is just simply interacting with the Coulomb Newtonian field of Alice's particle is just determined by the orthogonality of his apparatus having measured either path 1 or path 2. Okay? Okay, now let's consider the case where both Alice and Bob perform their experimental protocols. So there are now what we'll see is two equivalent points of view, entirely equivalent points of view on the cause of her decoherence. Consider a time, Cauchy surface, where sigma 2 that goes to the future of Bob's experiment, but the past of Alice's recombination. Okay, so again, I'm a relativist, so I get to draw my times any way I want, and I'm deciding to pick a time that's to the future of Bob, but the past of Alice's recombination, this kind of wonky time like this. What is the quantum state at this time? And I've really just said, you know, imagine the universe, I'm asking what is the quantum state at this time here, right? So I've cut off, the rest of the universe is irrelevant for this discussion now. And I've really just zoomed in on this region. What is the quantum state on this time? Well, in this time, Alice hasn't even started her experiment yet, hasn't started the recombination yet. She just has these stationary Coulomb fields. And Bob is simply, all he sees is the interaction of this stationary Coulomb field of Alice's particle having either gone to the left or gone to the right, and gets displaced in exactly this way as before. And the decoherence at this time is simply due to the orthogonality of the apparatus that Bob is measuring. I'm showing this particle displacement, but obviously it could be anything at this stage that he wants to, any apparatus he wants to use. Okay, so that's the story here. From this viewpoint, Bob is entirely responsible for the decoherence of Alice's particle, resulting in the paradox, which again is why I'm giving this talk. Okay, but now let's do a twist on the story. Consider a Cauchy surface that goes to the future of Alice's recombination, but the past of Bob's experiment. Wait one sec. Somehow that didn't, this is gonna be bad, 1 second. Okay, somehow the slides got out of order, but let's go here. The future of Alice's recombination, but the past of Bob. So this is to the future of Alice's recombination, but the past of Bob's experiment. On this time, we decided that all of the path information is now contained in the radiation states. They're not contained at all in the Coulomb field of Alice's particle. That's all just sitting here. That contains no which path information. All of the which path information is contained in the radiation states of Alice's particle. And if you allow me to now page back. So if we now, from this point of view, Bob is merely measuring the photons and gravitons emitted by Alice. So if I now apologize for moving back and forth so much. So what's happening here, if I now take the quantum state and do the joint evolution of Alice, Bob, and everything, Alice isn't evolving at all. Her radiation state is evolving, and that's all that Bob is measuring. It's just the which path information contained in the radiation of whether or not Alice went left or right. There's no Coulomb field in this description that contains any which path information. Okay? And the key point is that both viewpoints are equivalent. You can view Bob as measuring the Coulomb field of Alice's particle or the radiation emitted by Alice during her recombination. And both viewpoints are entirely equivalent to each other. And in the last 5 minutes or so, let me just now say this other viewpoint, the second viewpoint, actually makes clear the conclusions of Belenkia at all. Well, if you consider now the joint evolution of Alice, Bob, and the radiation state, so now on sigma 1, so what is sigma 1? Sigma 1 is this surface here. So that's, again, we have Alice's particle that's recombined, so these wave functions are exactly the same now. This should be down instead of up, I apologize. And there we have these radiation states, psi1 and psi2, that contains all of the which path information here. And Bob is just about to start his experiment. So therefore, he has, he hasn't turned on his experiment yet. Now we consider the evolution of the quantum state from sigma 1 to sigma 3, which is to the future of both Alice and Bob. So this is to, yeah, this really got messed up. Okay, well, anyway. So to the future of both Alice and Bob recombination. So if we do the evolution from, from sigma 1 to a later time surface, sigma 3, which basically encapsulates both Alice and Bob, well, the radiation states will interact then with Bob's particle. So they're going to interact and cause Bob's particle to get, to go into state B1 or state B2, and psi prime basically corresponds to the, the radiation state after interacting with Bob's particle. So Bob could absorb a photon or not absorb a photon, so forth, and you're going to get a different radiation state if it had gone on path 1 over here or path 2 over here. We don't really need to compute their interaction for this argument. We just have to say that there's some new radiation state created by Bob interacting and going from B0 to B1. And under the unitary of the evolution of the system from sigma 1, the surface to the future of Alice's recombination and the past of Bob to the joint future of both of them, implies that these inner products are equal to each other. So the inner product of the radiation states on this later time with the orthogonality of Bob's apparatus is equal to the orthogonality of the radiation states as before. This just comes from unitary evolution of the joint dynamics. But if that's true, that means that the orthogonality of the radiation states is always less than or equal to the orthogonality that Bob could go into himself, which means that the decoherence of Alice is always greater than or equal to the decoherence due to Bob. This is not mysterious. If you just view Bob as measuring the radiation from Alice, his apparatus cannot become more orthogonal than the radiation states are from the beginning. That's all this inequality is saying, and that's what this argument is pointing out. Okay? Okay, so let me conclude in the last few minutes I have. Well, if both Alice and Bob follow their protocol, then Newtonian mediated entanglement, this picture, that viewpoint 1 that I had before, and on-shell graviton entanglement are entirely equivalent to each other. And indeed, the second point was crucial to realize the resolution of the paradox I gave you before. And indeed, it is essential that point 1 and 2, or alternatively neither 1 nor 2, are valid descriptions of the entanglement in order to provide a consistent description of a quantum superposition that's consistent with causality and complementarity. Okay, so additionally, what we've shown is that this decoherence due to Alice is always bounded by the decoherence due to Bob. This is generalizing the analysis that was done by Belenky et al. And really giving a strict inequality between these two descriptions using this viewpoint. And what is interesting in the last minute, let me just point this out, you could read this in two directions. And the read in the other direction is possibly the most interesting. If you have a situation in which Bob can make clearly a discerning measurement of Alice's superposition, that bounds the coherence of Alice, right? This implies that any quantum spatial superposition must be at least as decohered as any Bobs at space-like separation that could decohere her. So let me give you an example that will tee up Dane's talk. So let's go back to the cartoon that I had before. I have this cartoon, I'll be done in a minute. I'll have this cartoon where Alice has this spatial superposition of this that she has before, and now she doesn't have just any Bob around. She has, well, a really worthy adversary, and this Bob knows, general relativity, okay? And what he's going to try to do, this Bob is going to try to do the same thing as he did before, but he realizes that, Alice has read our paper. She realizes that, she's going to go and check the other labs and make sure that no one's in those other labs that are over at space-like separation. But Bob realizes, well, I don't need to be in another lab. What I could do is I could just form a black hole. And I could just go and be inside this black hole. There's the long-range fields of Alice's particle have no trouble penetrating into the interior of a black hole. And Bob unfortunately won't have much time left to do the experiment, but he should be able to get some Witch path information of Alice's superposition in the interior of said black hole. And thereby, well, from the conclusions I gave you before, if Bob Wall now can get any Witch path information into the interior of this black hole, that means that the mere presence of the black hole must decohere Alice's superposition on her own. What would be the cause of this decoherence? Well, any real physical material body would decohere, like, if I make a superposition and this chair is over here, the superposition is influencing this chair a little bit differently if my superposition is over here than over here. And gravitationally, what I'd be doing is gravitationally interacting with the internal degrees of freedom of that superposition. Well, in the case of a black hole, that's not so obvious what those said internal degrees of freedom would manifest or even correspond to. What's the local description of Alice interacting now with this kind of inert black hole? And as Dane will explain tomorrow, a black hole will indeed decohere a quantum superposition as if it does contain internal degrees of freedom, and Dane will tell you more about that. Okay, with that, I think I'm a little bit over time, so I'll end there.
So wonderful talk. So for me, this is a virtual proof that low energy gravitons must exist in order to keep consistency of general relativity and quantum mechanics. Do you agree with that?
Everything I was saying was in the context of studying linearized quantum gravity, and I was arguing that there are fundamental, what are the key features of such a theory that you need to avoid. The only reason I don't go far as proof is because I don't know everyone's favorite theory of quantum all I'm saying is that whatever your favorite theory is, subject it to this Gedanken experiment and tell me how it's resolved. Because if your theory claims to not violate causality, then some version of this some of these key features, if they're not present, for example, if you claim that you don't have gravitons, but you just have Newtonian entanglement, gravitons can't mediate entanglement, and your theory has that feature in it, I would think this kind of protocol makes it very hard-pressed, I would say. I just wouldn't say proof, because I'm not so imaginative. Did you say virtual? So I don't know the definition of virtual, and so I think since I'm on record, I'm not going to say any more than I had currently said. Yeah, go ahead.
Yes, thank you for the nice talk. So coming from quantum information, people talk about no cloning and no noiseless amplification and monogamy of entanglement as consequences of non-signaling.
Yeah.
Can you comment a bit? Is it related to this?
That's a bit different. I mean, there are violations of causality, like these EPR pairs and things like that. But notice in this context, both Alice and Bob are not entangled initially. So it's a bit different. You can talk about, if you could invariantly talk about the degree of freedom, which is the Coulomb field of Alice's bar, that's really what Bob is entangling with. And perhaps there is a description of this language, but you would really have to go into the full realm of quantum field theory to make that precise. And you have these gauge constraints versus propagating degrees of freedom that you need to identify. So I wouldn't go so far as to say that they're unrelated, but I also wouldn't go so far as to say that they're directly applicable. Yeah.
Okay, really short. So this last statement that you have,
Yes.
As I understood, the coherence due to Bob was due to the interaction with the vacuum fluctuations of his electromagnetic field.
So in this context,
Yes.
Yes, the vacuum is playing a key role in the black hole case. Is that what you're talking about? No.
There's the following question. So in the black hole, what you're calling the supposed internal degrees of freedom would be equivalent to these vacuum degrees of freedom on the previous example?
Well, okay. I mean, let me back up. So Bob is in Bob Wald is in the interior of the black hole. Mm-hmm. Okay, and now, I mean, if the black hole is big enough, you can ask, like, does Bob have enough time to integrate his experiment beyond a local vacuum fluctuation here? And if the black hole is big enough, he does. I mean, he's not going to be happy about it, but he does have enough time to integrate his experiment beyond a local vacuum fluctuation here. So the constraints on Bob are not, that I was highlighting in flat space-time, are not relevant in this discussion. The constraints on Alice are also not relevant. Alice has the entire time duration of the existence of this black hole to do the experiment slowly enough. So she can avoid emitting basically any radiation to null infinity. Outside in the exterior of the black hole, she just has to do it within a time scale less than 1/g Newton, right?
Yeah.
So neither the constraints from Alice nor Bob that I was highlighting before apply to this case, which is why we decided to write it up separately. Yeah.
There is one thing I said it would be the last question, but I didn't know there's questions on Zoom, which I apologize. So I guess there is at least one question from Zoom I would like to take. Anupam?
Okay, so thanks Gautam for a very nice talk. So one question which is not very clear to me is that for all your arguments, you don't require gravity to be quantum. So where do you show where gravity is quantum?
Sorry,
Actually, I mean, the quantum gravity is quantum in your case.
The quantum nature of gravity is playing a fundamental role at almost every slide. So I don't have my slides.
I'm afraid, no, I don't see that. I don't see that where the quantization is required.
Well, in the emission of gravitons, for example, arguments
that can happen classically even.
No, absolutely not.
Classic. I mean, black hole merging of two black holes are emitting.
No. Sorry, these are coherent states of the quantum field, and the failure of them to be. Wait, if you'd allow me to complete the argument.
It was shown by Gupta and Kibble and Feynman and many others, and it's a textbook story that once you put gravity and matter, you have to quantize really the true dynamical degrees of freedom. So where is the dynamical degrees of freedom which you are quantizing?
Yeah, well, we are quantizing the massive degree of freedom as well as the radiation. I mean, if that's not clear from the if that's not clear from the slides, I think that's going to require a longer discussion than what we could do right now.
Sure.
Yeah, this is a big controversial topic with, unfortunately, we're running out of time.
Okay, if I could put my 1 cent in, I wouldn't claim that this is a controversial topic. But okay, maybe. Oh, Sugato, I think, has a question.
Yeah. Okay, please go ahead, Sugato.
I'm aware of the time, so it's a quick one. So can we? So why are you stopping short of telling that? Using the additional logic of this J. Duncan experiment,
yes.
When we get Newtonian entanglement, we can conclude that gravity is quantum.
Well, okay, yeah. The only reason I stopped short of it is because I am not nearly as imaginative as my colleagues in terms of what kinds of theories of quantum gravity you could make up. I don't know of a theory of quantum gravity where you don't introduce quantized degrees of freedom already. If one has such a theory in hand, then they would have to. So it's more of like what your model of reality is and your model of the experiment. I'm claiming essentially any model that you make up would be hard pressed to resolve this experiment essentially, or this Gedanken experiment. And I would certainly say that this is strong evidence for the existence of the graviton. If one succeeds, as most people are trying to do, measure the gravitational mediated entanglement. So I would go so far as to say it's extremely strong evidence. a proof is a mathematical statement that is harder to, I mean, you have to state your assumptions. And if your assumptions are already a theory that contains gravitons, you know, it's hard to close this circle, right?
Okay. All right, let's thank the speaker.